modern fancy materials for multitude of applications, photovoltaic, light emitting, and sensors. And there are like hundreds and thousands of papers. So one of the directions pursued by Aaron is to look at ability of perovskite nanoparticles to emit light, and he's observing the trend that presence or absence of ligands on the surface of nanostructures strongly affect their ability to emit light, and therefore partially he was doing computational surface chemistry for looking of absorption energies. So it is not exactly what group of Professor Brookhouse and Steven are doing, but there will be some connections. Okay, please go ahead, with understanding that we have total 3 presentations.
Yeah, so that was basically the introduction. I didn't put anything about absorption and emission characteristics depending on ligands. I just focused on the surface chemistry of ligands binding to a perovskite surface. So my first title is more general because I thought about adding more stuff, but so the focus will be cesium lead bromide nanocrystals and then binding of ligands to their surface. So
it's fine, it's fine. It will come up back.
Right. I was going to talk about a figure, but it's kind of pointless to talk about a figure if other people can't see it.
Okay.
Yeah, we have a printed one, so you can.
Yeah, I guess that too. So in the literature, there's a kind of a conventional ligand scheme for how these perovskite quantum dots are capped. So during the synthesis process, you have to use both oleic acid and oleoamine to dissolve the precursors, and it turns out that both of those can bind to the nanocrystal surface. So that's this region right here where you have the oleic acid gets deprotonated, and it protonates the amine, and they're charged so they bind to the surface, and that's one of the possible binding scenarios for these crystals, and that's the main one I'm going to focus on because that's what my modeling primarily focuses on. And that's this slide here. So you can see this ligand combination we use to passivate a lead halide perovskite nanocrystal. Where you see the inside is made up of a 2 by 2 by 2 units cell, which is about 1 nanometer wide for a perovskite quantum dot. And then for all the surface leads, there are these small chain acids. I guess you could call it like a formic acid. So,
or it is formate if it is without.
Yeah, formate. Yeah, so it's the charged ligand.
It's not formate; it's acetate. If in your work.
Acetate, yeah. So an acetate anion binded to the surface leads, and then the surface ammonium groups, they bind to, or they don't bind necessarily the surface leads, but they kind of coordinate with the surface bromines, and they kind of alternate throughout. So it's kind of hard to see from this picture, but usually these amines, they cover the faces of these perovskites and they replace the, like where the cesiums normally would be. So
is that amine is as a counter ion for the ligand, or is binded on the surface to perovskite?
So it is binded to the surface a little bit, and it is a counter charge too, because it gets charged from the acid. So they're kind of correlated in a sense, and I'll get into that further.
So it's not just for balancing the charge; it also has interaction with the ecosystem.
Yep, it mostly serves as a structural feature, because on the next slide, freaking PDFs.
I don't know why it's happening every time in the.
It's because I make it a PDF every time.
It's going forth and back between Mac and PC.
Yeah, but I guess the figure's not really the important thing. That just shows the density of states for the system.
Every time it's like 15%, so 90-degree angle.
Or it's a partial density of states. So you can see in the valence band. I don't have my key. So this black dot is the total density of states. The red dot represents the halide electronic density states. So that's the bromine in this case. And this green and pink figure kind of overlap with each other, and that's the ligand binding to the lead surface, which is shown on the right. So this is the most important part of this figure. So we do see that there is from our DFT calculations anyway, there is a chemical bond between this acetate anion and the surface of the lead. Whereas we don't see that with the protonated amine. It doesn't provide any electronic density.
That ligand has a pretty strong contribution close to the band gap.
Mm-hmm. Yeah, or well, I guess it's, if you scale it, it's probably like maybe 10% of electronic density is on the ligands. Because you can kind of tell from this inside middle figure too, because on each of the faces, there's a little bit of that, of the oxygen binding to the surface. And they kind of act like, for your envelope functions, it's like, it acts as like the tail of the envelope for each of the sides. So, the thing to take away from here is there's chemical bonds at the surface between the acid and, or the deprotonated acid in the surface. And so, generally, the possible ways that this acetate anion can desorb from the surface, it's usually due to protonation, just because they're in they're colloidal systems, and so the acid-base equilibrium like mostly determines what type of bonding we have on the surface. So if you have these acetate anions bonded, it can either, or the two ways that I see that can desorb, it can either take a proton from the protonated amine that's in the vicinity of it, or it can just grab a hydrogen that's hanging out somewhere in the solvent sphere and just randomly comes in. And the acetate ion could take that one as well. And so those are kind of the two general schemes that I thought of when trying to compute binding energies. So when I do my binding energies, I include the protonation effect too, because it's not going to deprotonate and then just stay as a charged, or it's not going to want to stay as a charged anion. It's going to want to take a proton from somewhere, or get rid of its charge somehow. And so when I do my binding study, so this is just another figure of the model, I consider binding to the 1,0,0 face of the surface. So if you just take this and kind of rotate it, that's what this figure is showing here. And so I remove the acetate anion from the center face, and then one of those protonated amines from one of the like adjacent spots that are covering the face. So does that kind of come across where I'm taking these ligands from?
Why from the face, not from the edge or corner?
Time.
But
I don't know if I wanted to do all of them.
But do you have expectations how it will differ?
It would be less binding. But the binding energy would be less, I assume. Because usually the corners are more reactive. So that's just my expectation anyway.
At least it will be different.
Yeah, it'll be different. But usually, like if you see like an experiment, if like the nanocrystals do coarsen, it's due to like the 1,1,0 faces, or like the corners of the crystals merging together. So that kind of indicates that like those are the weak binding spots for the nanocrystals anyways on the corners. And so these are just kind of chemical equations representing each of the three calculations I did. So initially I start all of them, or the first scenario is removing one of the acetate anions from the surface. So I start with a fully passivated crystal plus the proton that's just hanging out in the background, which I'll include in a little bit. And so over time, this acetate anion will pop off the surface, so that will change the charge of the nanocrystal. And if it interacts with this hydrogen that's just kind of hanging out from, that just randomly collides into it. And then I calculate the protonation of that anion. So that's the first calculation I did. And the second one, I just did the same thing for the ammonium, except instead of protonated, I deprotonated it as its final, as its final state. And then the last one, I removed both the ligands simultaneously and did geometry optimization where they were close together, kind of simulating if they flocked together, how the, like what would the relaxation energy be if the acetate ion just took a proton. from that ammonium group. And so just to kind of summarize how we're viewing these calculations. So the left side is calculations 1 and 2. And if you consider those as like being stepwise, so here you have the ammonium coming off and then it deprotonates, and then that proton can go to another nanocrystal and take another acetate anion. So if you add both those energies together, you would have like the total amount of like uncorrelated desorption. If that makes sense. Or like if you had two independent processes happening compared to if you had correlated desorption, where you had both of the ligands flock from the same time, and then the acetate anion just taking a proton from its neighbor. And you can compare the binding energies to see which process will be more favorable for deabsorption. And just for notation, I took binding energy as the energy of all the product states minus the energy of all the reactants. So that way, that if our binding energy is positive, that would indicate that the ligand staying on the surface will be more favorable than coming off the surface. And the last slide of results, this just kind of summarizes everything I've talked about, and then this table shows the binding energies for each of the calculations I showed. So this first one of removing the acetate ion and then protonating it, our DFT calculations showed that it's actually, you get a negative binding energy. So it's actually more favorable for that acetate anion to be protonated and insolvent than being onto the surface. And then the second calculation, just removing the ethyl ammonium and then deprotonating it. So that had a positive binding energy of about 3.61 eV. So that kind of indicates that the charge attraction is pretty strong regardless of whether it's protonated or deprotonated. And then if you add these two together, you get the like the uncorrelated desorption energy, which would be 3 eV. If you compare that to the correlated, which is removing both of them simultaneously, and then the anion getting deprotonated, or deprotonating its neighbor ammonium, you get a binding energy which is less than these some. So that just indicates that it's more likely that if your ligand's going to desorb, it takes a proton from its neighbor than from the solvent. And yeah, so a summary, looked at the binding energies of two common ligands that are common for surface termination of lead halide perovskite nanocrystals. And we looked specifically at removing from a 100 phase, where you could also look at 110 or different phases of the crystal. And the main finding is that the acetate anion would rather be protonated if it had the choice than being stuck to the surface. So if it finds a proton from solution, it's going to flock or desorb from the surface. And then just due to the way that these things are synthesized, there's adjacent protons pretty much everywhere on these crystals. So it's kind of it's a very dynamic and unstable binding situation for these things. And yeah, that was my last slide.
Okay, let's thank Aaron. Other questions?
What is the motivation again for doing that?
Motivation?
I guess
I'm not in that field, right? Not really. So for me, it looks like two weird molecules absorbed in another weird system. So, but I'm not an organic chemist.
Neither one of us.
I guess there is a motivation of some sort for
Yes.
for what is
I would be happy to answer unless Aaron wants to.
I guess very broadly, these are relatively new class of systems. They were only first synthesized in 2015, and there's still a lot of open questions of the surface chemistry of these. And there's a lot of reports, like experimentally, that if you do, it's like some NMR experiments called Drowsy or whatever, but basically you can kind of track like the ligand passivation of these things. And experimentally, they find that it's a dynamic bonding of the anion or the acid, so it's constantly popping onto the surface and then coming off and then flocking on and off. And so
it's a part of decomposition. process?
Or it's the, I would suspect the protonation.
Well, this is more technical, global. What is? Let me try and do compliment. We want to sell quantum.tv made of perovskite eventually.
So that is quantum dot.
It is those are quantum dots which are able to emit light. If surface of quantum dot is missing ligand, it quenches luminescence immediately. So it will create surface trap. The charge will leak through like empty, not covered spots on the surface, and it will stop emitting. So it will be not considered as a good emitter anymore. Therefore, there is a synthetic effort to prepare quantum dots carefully covered by ligands of this carboxylic nature. Am I right?
So there's kind of stability issue down here.
Stability.
There's a stability concern of the systems and some way.
Yes.
And
Well-
there are 5 million different ligands in organic chemistry, I guess, or 10 million. So why use exactly these two? That's-
Because they found, so the precursor is a lead halide, and they found that the only way to dissolve it is if you have both the amine, or both of these type of ligands. If you only included like the oleic acid, you can't dissolve the precursor. So it's a necessary part of making the crystals, or the synthesis. When they first initially did it anyway. There have been other attempts at different ways to make the crystals, but this is still kind of the one most reported in the literature, or that most people use to make their dots for their experiments.
So, I don't know if it will be ever useful, but maybe we can like find some overlap between these two projects. So some direct measurements of binding energy of ligands in vacuum may eventually guide synthetic chemistry effort to prepare these shiny nanocrystals.
The problem for us is the quality of the samples in the first place. So getting a binding energy is pretty simple, right? A simple experiment. But the starting material is not really clean, right? Because that is a kind of on-air made crystals. That was the first paper, right? There's a lot of CO2 and water absorbed and that. So we would like to have a study like that, then we have to find a way to get better samples somehow. I'm afraid, otherwise you always absorb on impurities, something.
So those experimental samples that Aaron is talking about are in colloidal solvent, in some like hexane or.
Yeah, hexane, toluene. But you can make films out of them, and you can even do ligand exchange.
But how to get in a vacuum chamber without contaminating the system?
Hexane is a big contaminant? Maybe just inject, just in, right inside vacuum chamber, inject this colloidal stuff on a substrate.
So you would like to make the crystal inside of the vacuum chamber? No?
Hexane is usually has a high vapor pressure, so it will evaporate quickly. Some kind of a liquid, like ionic liquid properties, without evaporation, if you want to study.
So it's not impossible.
But a liquid phase synthesis inside of a vacuum chamber.
No. One does chemical synthesis in a beaker, in container, has it as pure as possible, and then you take a sip with syringe and inject inside your vacuum chamber so that it doesn't contact air at all. And then this hexane evaporates, and there will be deposition of.
Maybe we are looking for something like that actually, but some synthesis like that. The injecting part is not that simple, right?
Okay.
It's not a GC or something. They have a kind of membrane, a stick a needle through a membrane that doesn't work in a vacuum chamber.
Okay.
But
Well, we can keep thinking of it as a probably next project.
if you have some kind of liquid, I guess we could build something like that. It's an interlock system of some sort.
Jared?
I have a questions on your calculation, binding energy calculations. So you have found that when you separate, calculate separately each ion, that's binding energy higher than compared to the correlated one. Is it because of the interaction between the ligands, or because when you detail just acetate ion is a huge binding energy, sorry, ethyl ammonium, is it because of just bond binding with the surface or binding with other ligands too?
It wouldn't be binding with other ligands because we don't.
Maybe because of that, when you calculate the binding energy for together, like correlated on acetate ion and ethyl ammonium, that's the binding energy pretty small because you separate a whole system plus and the counter ion together. But before that, that ligand is interact with the surface and other counter ligand as well. So that's why very high binding energy. So it's not just surface binding energy, I guess, maybe.
Well, I guess it is an ionic interaction, and usually, like Coulomb interactions, like bond distances are, I think, like 5 eV.
Okay.
So, I mean, the methyl ammonium, it doesn't do any chemical bonding, so it is purely electrostatic.
Oh.
So it would, like, if you didn't know anything about it and you were just trying to, like, put an order of magnitude estimate, what you think the binding energy would be, it would be on the EV range.
So another thing is it average binding energy or just one ethyl ammonium?
Just one, so it's just from that site. So that's the binding energy is from that one site.
Can you go 3 slides back? So what if you remove all ligands except last 2, except one acetate and one ethyl ammonium? What would be their binding energy? Would it be weaker or stronger?
Depends on the surface of the perovskite does.
Well,
Like,
to the same surface as you did this computational experiment.
I guess it would be less because it doesn't have any interaction with anything else, like any of the second sphere of ligands that are surrounding it.
No.
So you think that second sphere is more attractive for the ligands rather than screening effect?
In this case, I guess I'm not sure, since it's a mix of positive and negative charges. I'm not sure how that would add out like over the entire field. And that we don't include like entropic effects, like the tails of the ligands, which would make it less stable too. I would assume, just because they're fighting for position.
Okay.
And I have another quick question, so I'm not sure. And in a DOS, it seems like ligands is contributed significantly on the close to the band gap. So, do you expect that there was some strong contribution on the transit, should I say, in the whole band during the excitation? So, isn't it supposed to be quenched with the photoluminescence? Because they're very light, small ligand molecule, they have a lot of different forms. So, shouldn't it quench the photoluminescence in this case?
Well, it would speed up cooling. I don't get why I would quench luminescence.
Or is make
Unless
any trappist state there? I'm not sure, I'm just wondering, because the ligand is contributed close to the band gap.
But not to the...
Oh, it's not inside the gap, though. So there's no localized state on the ligand.
So this partial charge density for HOMO shows that there is nothing on the ligand, everything is inside the gap. So it's very favorable for photoluminescence.
So yeah, so it might be, like, usually if you think there's any electron density on the ligand, it might be a trap state. But in this case, it's just hybridizing with the surface.
Hybridizing.
So it's just, so you can view it as part of, like, your 1s wave function.
Oh.
more questions to Aaron? If not, then thank you once again.
What is the advantage of a quantum dot TV, by the way?
It is really brighter for human eye. It is more clear.
Okay.
So it's like old photograph becomes blurry and not as
small
not as
pixels.
bright. But if it's like very new photograph and 100 years old photograph. So quantum dot TV is really.
It's a pretty good TV. So look at it, you have lots of large too.
And also it's not that bright. Pixel is not that small. Quantum dot is very high pixel. You will get high number of pixels.
Okay.
So it's very fun activity to go to like Best Buy. And where they try to sell these things, they put them near each other. Huh?
Can you buy that already?
Yes.
Yeah.
Not from perovskites, from yes.
Oh, yeah.
It's like indium
Somebody has
phosphate.
Thank you.
Okay, cool. So it is human eye can see the difference,
Okay.
and especially human eye can see the difference in prices.
Yeah.
So they have already one of them at Best Buy already?
Yes, yes.
Ah, I should go and have a look.
Yeah, even if not buying, just walking around and see how different technologies are. So they put them in ranks like OLED, quantum dot, and old-fashioned.
So how much is that?
What's the price range?
It's like when you ramp up between
Yeah,
different
but
technologies,
because,
it doubles the price.
It doubles, okay.
Like 60 inch.
The
like
doubling is
six-
not so
more than
bad,
1,000,
right,
yeah.
actually.
More than 1,000.
60 inch.
Yeah, so we studied absorption of formic acid on methylammonium lead iodide perovskites. So I'm going to summarize the major results of our experimental project.
Keep going.
Yeah. So the main objective was to improve the stability, thermal stability of the perovskite, methylammonium lead iodide perovskites using a passivation layer of formic acid adsorbed on the surface, and we synthesized the perovskite structures at ambient conditions using like some kind of a spin coating method. So we synthesized the perovskite structures, and we characterized those structures using standard techniques like UV visible adsorption spectroscopy, scanning electron microscopy, and X-ray diffraction. And after characterizing those samples, we put those samples inside ultra vacuum chamber, and we studied the thermal stability and the adsorption kinetic studies at ultra vacuum conditions. So at ultra vacuum conditions, we characterize the sample composition, elemental composition using OG electron spectroscopy. So here you can see the OG electron spectra of the perovskite samples, and as you can see, we have the elements lead and iodine here, but we have huge amount of carbon and oxygen. So during the ambient pressure synthesis, there can be like huge amount of carbon dioxide and water adsorbed on the surface, and because perovskite is susceptible for the absorption of carbon dioxide and water. And we also saw when you do the thermal desorption studies and stability test, we see huge amount of carbon dioxide and oxygen water desorbing from the surface. So this may be most likely due to the adsorbed carbon dioxide and oxygen. And also there can be some impurity carbon, residual carbon deposited on the surface. So even though we need to have an ideal surface like this one without any impurity layers, we have some impurity layers on this perovskite film, unfortunately. So we did the ambient pressure synthesis using the indium, using a substrate which was coated with indium doped tin oxide, and that substrate we cleaned with again at ambient conditions. So we couldn't remove all the carbon impurities, So the substrate itself can contain some carbon, and then the perovskite layer after synthesis and during the synthesis it can be contaminated with those atmospheric carbon dioxide and oxygen. So we have a lot of carbon dioxide and oxygen adsorbed on the surface initially, and we tried to remove those impurities by flashing at ultra high vacuum, and we tried with sputtering with argon ions, but in both cases, if we flash the samples to higher temperatures, then it tend to get destroyed. So we couldn't go beyond like 400 Kelvin, even 380 Kelvin. It start to deform the film. So we don't wanted to dissociate those films. And so we studied formic acid adsorption using thermal desorption, using a thermal desorption technique, and this is the experimental setup here. And here this is the perovskite sample, the perovskite thin film, and initially we kept this perovskite thin film around 100 Kelvin and at very low temperature, and we dosed formic acid inside the vacuum chamber using just backfilling the vacuum chamber, and at that kind of a low temperature like 100 Kelvin, the desorption rates are minimum, so we expect the formic acid adsorbed on the surface, and then we linearly ramp the surface temperature, and the desorption fragments from the formic acid, adsorbed formic acid, were detected using this residual gas analyzer, mass spectrometer. And these are the formic acid gas phase mass scans, and we detected 4 different. Yeah.
Is it okay to interrupt?
Yeah, no problem.
So how you were talking about it half a year ago, but how quick do you ramp the temperature to cover the?
So it is about like 1.6 kelvins per second. So that was the heating rate.
Okay.
Yeah. So it was we could change the heating rate, but that was the heating rate that we used.
And you expect that slight change of heating rate will not affect the?
If we apply high heating rate, then the thermal desorption spectra would looks like different. That means the peak broadness can be changed here.
But we can change it by a factor of 10 or not
Yeah.
even, right? So you use what, 10,000 Kelvin per millisecond or something?
Yeah, something like
Yeah, we are never getting close to it.
And these are the fragments that we collected, the fragments, and these are the thermal desorption profiles that we collected during the thermal desorption experiment. And here you can see the thermal desorption spectra as a function of surface temperature here. And at lower temperatures, we could detect the molecular desorption of formic acid. So we dosed about 20 Langmuirs of formic acid, and this lower temperature desorption peak may be mostly due to the molecular desorption of condensed formic acid on the surface. And then at high temperature, that means around 600 Kelvin, we see 3 different mass fragments here. So if we compare the gas phase mass scan, so we have very small intensity of this formaldehyde fragment, but here in the multi-mass TDS scan, we have huge intensity of this formaldehyde fragment. So that means the formic acid adsorbed or desorbed dissociatively during this thermal ramp. And the intensity of this molecular mass fragment of formic acid is relatively low at high temperature, but we can see a small amount of molecularly desorbing formic acid parent mass fragment, and this can be mainly due to associative desorption of this adsorbed formic acid. And based on the
Can you interrupt? I just do not. Can you please indicate relative height of the decomposed of this HO and original formic acid?
So
relative height? It should be in the bar diagram or not?
Yeah, maybe in the bar diagram.
Yeah. So you, what was your? Can you
Repeat. So on your left side, bigger figure,
Yeah.
it looks the blue line
Yeah.
is HCHO,
Yeah.
product of decomposition,
Yeah.
and it is higher than any other products.
Yeah. And so you're talking about this fragment,
Yes,
right?
yes.
Yeah.
And at which is there any temperature regime when formic acid decomposes without chemical? When it is not decomposes but just desorbs?
So it is like this is the parent mass of formic acid. This intensity was very low compared to this intensity.
So yes.
Yeah,
So
yeah.
how much less? It's like 100 times or million times?
There was a scale factor.
Yeah, there is.
Yes, scale factor.
Which was 200 or something.
Yeah.
It's not
Okay.
much smaller.
So exactly, I don't remember the factor
Scale
here.
factor is missing somehow in
Yeah.
the picture.
Okay, so 2 orders of magnitude.
Yeah, I think it was 200, something like that. I have to check.
Something like that.
So there is a molecular absorption channel, but a very small one.
Very small amount. Yeah.
So,
All right. Okay. So we compared the gas phase mass scan and the.
So even
yeah.
at low temperature, there is some dissociation of this molecule.
So you are talking about the dissociation temperature range.
Yeah.
So we see the desorption around 600 at that time temperature of about 600 Kelvin.
And there is a feature at 200?
It is
I guess the question is, what is the dynamics actually of the process? What? So does it dissociate on impact or is it thermally activated? And I don't think we can really say that.
yeah, we can have both on impact.
Oh, so you're telling that it may dissociate right when you deposit?
It looks like it dissociates at low temperature, and then the fragments are bound on the surface
Yeah.
with a relatively large binding energy.
And then
What you see dissolving are the fragments, right?
Okay, so it likely dissociates immediately, but wait a second. It's chemically breaks but doesn't dissolve.
I would guess because you have dosed the gas first, right, and then you ramp up the temperature. It's not a steady state experiment. One could do a kind of steady state experiment, right? Dose the stuff 10 minus 8 and then you ramp the temperature. We have not done that, I'm afraid. So he dosed first the gas and then he ramped up the temperature.
Okay,
So there might be molecular precursor for the dissociation. I guess because you see molecular peak, right? But I guess the desorption, the dissociation must be before 200 Kelvin or something, right?
and those fragments adsorbed on the surface at submolar range. So below the monolayer range, it has a high binding energy, so it needs high temperature for the desorption. But at
yes. Aaron, do you remember my question to your presentation, last question? So it is what Tilan is telling right now.
I just spaced out for that 10 seconds.
Okay, so adsorption energy is very different depending on concentration of ligands.
layer.
So if the concentration of ligands is less than 1 monolayer, less than full coverage, is much higher, and when it is fully covered, it becomes almost not dissolving, or well, it differs from case to case. Is it right?
It's case. It's kind of.
Okay.
So but you dosed 20 nanometer or something, right?
Yeah, huge amount.
So you started with a saturated surface, I guess?
So that's why we see a
You
huge
ramped up the
peak at
temperature.
this lower temperature range.
So I don't know if we can figure out the dynamics of the process. And if you do molecular dynamics, time resolved, you could actually see if that dissociates from impact, or so you could do a calculation like that, right?
Yes.
Qualitatively, at least,
Right.
which would
Yes.
tell us what the mechanism is, right? Is it some kind of precursor mediated dissociation, or is it on impact?
Impact, yeah.
So we can assume that there is a kinetic energy corresponding to about 200 Kelvin. So just the impacts with this low momentum, and maybe this energy is enough to break the mold.
I think the activation energy cannot be higher than that, right? Otherwise the precursor would be gone already. So it must be somewhere 220 or whatever that is.
Close to 2.
Activation energy must be smaller than 220 Kelvin. what gets according to the.
Okay.
Okay. So the same thing it is formulated in a different way here. So we have the gas phase mass scan here, and then the formic acid, the collected mass fragments. This time those fragmentation peaks were integrated and the intensities were normalized and put in here. So if we if we have the molecular desorption, we should see the similar kind of intensity ratios of these peaks in both cases, but the gas phase mass scan and the collected formic acid fragmentation pattern has two different intensity ratios. That confirms the dissociative adsorption of the formic acid molecule.
So at the right you have two figures.
Yeah.
So
it's the same thing like the.
What is the difference between top and bottom on the right?
In the top, here we have the gas phase mass scan of formic acid, top one. At the bottom.
And probably, I don't know, it would be better if you introduce what is gas.
So it is like without the without the perovskite layer, we just dose the without the perovskite film on the film, we just dose formic acid into the vacuum chamber and we just collected the mass scan of that. So it is the characteristic mass spectra of the formic acid.
So it decomposes even without perovskite.
So it is like this is the mass scan of perovskite. It's like when it collects even any kind of a mass spectra, it has a fragmentation pattern. Even water has fragmentation patterns at different, like it has the parent mass of 18, it has H2O which correspond to 18 mass, and then few different masses, 17, that means deprotonated water. So each of those molecules can have different fragmentation patterns. And the intensity ratio is the most important thing. So if we don't have any kind of dissociative adsorption, we can like if we don't have any kind of dissociative adsorption, we should see similar kind of fragmentation pattern characteristic to the gas phase mass scan.
So this pink stuff is like a background, a baseline.
Yeah, something.
That's just the gas phase.
Gas phase, yeah.
And any
you can look up in this database also.
Yeah, that one also here.
So deviation of your results from this baseline will be the effect of perovskite.
Exactly, yeah.
Any mass spec is dissociated. That's how a mass spec works, right?
Yes.
So the deviation is the effect of the perovskite layer.
Deviation from this.
So if the dissolving thing looks the same as a gas phase, and you have intact molecules which enter the mass spec.
Yeah.
So you have a molecular adsorption. But if the patterns are different, then you have already fragments which go in the mass spec. Then you have some dissociation going on.
I see.
And the parent mass can only be the original molecule, right? If it looks at parent mass, and that is what you saw on the inside, right? It was a parent mass of the.
So in the.
That must be molecular.
And what is shown on the top right is that.
So the one is a gas phase. I think the top one is a gas phase.
Yeah. So there is fragmentation even without any perovskite. Just mass spec itself, or maybe chamber induces some sort of.
You can look up some in a database. In this database.
So this is from a database. This
the
is
bottom
from
is
the
a TDS, right?
Yeah, this is from a database, the gas phase mass spectra of formic acid, and we have a similar kind of mass spectra. Here, this is our experimental gas phase mass spectra of formic acid. It's kind of qualitatively similar, and the higher mass, the parent mass, have a small intensity here because we have a small, like some kind of a sensitivity issue, but it's qualitatively similar, I guess.
It depends on the ionization energy of the mass spec and so on. So that's why it does not look exactly
the same, but it's kind of qualitatively same.
Also, mass spec is dying, I'm afraid. So the sensitivity is getting worse with larger masses. Sensitivity is decreasing. So if you have an old mass spec, then the high masses show up as small intensities. That's the point where you have to start writing grant proposals.
Instrumentation.
Getting more equipment.
proceed?
I'm okay.
So based on our results, we just proposed a small mechanism for the dissociation, and these are based on the desorption fragments and also some experimental and theoretical findings. And here the formic acid can adsorb molecularly, so molecular adsorption molecularly, or it can also dissociate on the impact. So it is difficult to distinguish between the adsorption and also, the way of adsorption, whether it is dissociated with the impact or not. And since we dosed a huge amount of formic acid, multi-layer adsorption may have the desorb molecular formic acid, and also as we saw from the TDS data, these molecular fragments can associatively desorb to form the parent mass, the formic acid parent mass. And also these adsorbed formic acid fragments can dissociate in different ways, but unfortunately it's difficult to distinguish those dissociated fragments with our experimental techniques. But in previous studies, these fragmentation patterns were observed for formic acid adsorbed on different reactive metal surfaces. And in our case, we have perovskites, and in the perovskite structure we have adsorbed water on the surface, so we can have OH and hydroxyl, and on our surfaces we in our vacuum chamber we have a huge hydrogen background, and because of that we may have some adsorbed hydrogen. So these are the possible fragments of formic acid and other background chemical impurities. So these fragments, when you heat the sample, these fragments can associatively desorb or molecularly desorb to form different kinds of mass fragments. So we detected these mass fragments labeled in the red color. So and based on our results, so we characterized the elemental composition before and after the formic acid adsorption study, and so here this is the oscillatoron spectra before and after formic acid adsorption TDS experiment. So during the TDS experiment, we ramped the sample temperature up to like 750 Kelvin. So we did this for true trials. That means we ramped the sample temperature from 100 to 750 Kelvin. After those two thermal ramps, part of the perovskite film seems to be destroyed, but we have a significant amount of this perovskite film even after those two thermal ramps. And we did similar kind of thermal ramps with a bare perovskite film without adsorbed formic acid layer. So after so when we heat those perovskite layers without those formic acid adsorbed layer, the perovskite structure seems to be destroyed after those thermal ramps. So that means the adsorbed formic acid layer has introduced some kind of stability for this perovskite structure. So as a summary, so we saw a dissociative adsorption of formic acid on perovskite, and it seems to be the thermal stability of the perovskite seems to be somewhat increased with this adsorbed formic acid layer.
Is it?
Yeah, that's it.
Okay.
Yeah. Well, thank you.
Because I have a question. So I guess the reaction pathway is very complicated. So could you please go through the reaction pathway again?
Can you ask it again?
Mechanism, I guess. That's it. So that is more from a literature mostly. Formic acid has been studied on any surface pretty much. It's a pretty standard system. So you can find that in the literature. There are also theory papers who came up with a 29 zinc formula. I think there's some on copper surfaces, right? They did some DFT calculations and saw apparently that formula is formed. So there's mostly literature, and he has seen all the red stuff that's showing up in his TDS. So that seems to match with that mechanism. So, more or less.
Yeah. The adsorbed state still we need to have some IR or any kind of
There
spectroscopy.
might be other ways of
Yeah.
options to. So that's where the theory maybe can help us to figure out what is the mechanism. Right? We have a problem with water impurities on CO2, right? We have no idea what is the water and CO2
Yes.
actually doing. We may need more data for that. So you
Yeah,
did
for
not look
example,
for
like-
water absorption.
Okay, okay.
But then you have to put in a sample and we can show again and so on, right?
You're getting ready to present? I want to ask some questions. Okay.
So we may need to look for more masses than what he looked for at the moment to address.
So like from here to here, do you need another molecule to participate in the reaction, like another water molecule?
That seems to be the standard step. So all people write that format is formed somehow. So we absorb formic acids and the intermediates you see with yields, for example, infrared spectroscopy, they say you see format. So that seems to be the standard intermediate which forms on
Kind of an
metal and
intermediate
metal
thing.
oxides. So
Okay,
nobody
so-
has done that on that system before. Right?
Like I would guess the formic acid like fizz absorbs to the surface or is impacted enough, and then once it coordinates to a lead, it's like the charged interaction would probably be more favorable than whatever hybridization. So it kicks off the hydrogen maybe. That's just a guess though.
So why format is formed, I guess you may find something in literature for more information about that. I did not spend that much time on literature. But there are 100 papers about formic acid absorption, at least I would guess.
It's not too many.
Not too many. So,
Technically possible.
so there might be some more information about that step if we look for it.
And also this is stepwise reaction from format to this fragment.
That is from that copper paper, I believe, where they came up with the DFT.
It's like so we exactly don't know what are the adsorbed fragments, and when the formic acid impact on the surface, it can adsorb molecularly because we have a polycrystalline surface. The surface have different binding sites. So depending on the reactivity of those binding sites, formic acid can bound itself, and formic acid can dissociate with the impact and then form formate and adsorb hydrogen, or it can dissociate further to form those kind of fragments. Those fragments, exactly, we couldn't characterize those fragments. We need some kind of IR spectroscopy or any kind of a technique to characterize those things. But only we could detect these fragments. Based on those detected fragments, we just assume these kind of fragments can present, and this hydroxyl and hydrogen, they can be from either from formic acid or from the surface itself, because surface has water, right? So water has hydroxyl, and in our we have a huge hydrogen background in our chamber, so hydrogen can adsorb on the surface. So those hydroxyl can be either from formic acid or from water or something else. But these fragments, we are not 100% sure, but in some surfaces, even in some other reactive surfaces, those kind of fragments have been observed. So that's why we guessed those are possibilities, but we are not exactly 100% sure about these adsorbed states of those formic acid.
But you get trend mass 29 and 30, right? That's what you see.
Yeah,
So
we
how do you-
have these things we detected.
So how do you form 29 on 30? There might be some other ways to do that.
Yeah. And even those molecularly adsorbed fragments can dissociatively desorb and form those fragments. Something like that can also possible, but still, like, we have to.
I think that is pretty much the standard mechanism found in the literature, as far as I can tell.
So this is not stepwise reaction, right? So
No,
this
no.
molecule can go to this one as well, right? Directly.
Yeah. So that was I was telling. So this can directly dissociatively desorb from those molecules. So again, it's like there are several different ways, but
I would maybe look in some DFT papers, so I don't know what guys have done before.
There could be DFT papers on other surfaces.
Yeah, there's one for copper at least. So I have not really looked for theory, right? I'm not a theoretician, so I would maybe look at what other DFT guys have done already.
I have a question, and I need to show something. Do I have permission to show page 2 of supplemental? Okay.
I emailed it around already.
Well, maybe it was just for like burn before reading.
I hope it's not that bad. That is from literature, right? That's
Yes, but could you please make just guide through this equations and tell how which reactions are more probable, how it connects to the diagram that you were showing? What is your vision of relative activation energies for different channels? Just basic.
I don't think, Tilan, did you read the papers? Not really, right?
I read the paper but not the supplement. But I can like go through the mechanism, I guess.
just
So the first step is it's actually so it is like molecular adsorption. Yeah, here this one we assume the molecular adsorption. The gas phase formic acid can adsorb on the surface, and this molecularly adsorbed formic acid can dissociate to form the formate and hydrogen, adsorbed hydrogen. This is one of the most common way of dissociation of formic acid that we found in literature. So we have formic acid adsorbed, and it can dissociate to form this formate and adsorbed hydrogen. And then when we ramp the temperature at high temperature, this formate ion and can form carbon dioxide and hydrogen.
So activation for first step and second step are different. Second step is needs higher activation energy.
Yeah, exactly. So we need to increase the surface temperature, I guess, to provide the activation energy. So then it can dissociatively dissolve from the surface.
So at lower temperature, it will be only this formaldehyde, and if you ramp the temperature higher up, there will be
formate ions. Yeah.
But for that,
And I don't remember exact temperatures here in this
for
case.
that you need a steady state kind of situation, right? That would not work in your experiment like that.
Yeah.
Because the stuff dissolves at 200
Yeah, these are just from the literature findings, I
So
guess.
that was some background adsorption, something like steady state type, I would guess.
So it is the main reaction for this work.
This is the second one. So
Yeah, the second one.
you have to look in the paper how they did that experiment. I guess it was some steady state. So they have a certain pressure in the chamber and then they heat up the system, something like that. Or it may be even ambient pressure or something, catalysis type study. Because your stuff dissolves at 200 Kelvin, so you wouldn't really see that, right? Because there's nothing, unless you have some background adsorption in your vacuum chamber.
And also the carbon dioxide desorption, we already have carbon dioxide in the film. It's adsorbed on the film.
That might be from different temperatures,
Different.
right?
Yeah, it can have different temperatures too.
It would be good to look, we don't have the data for that. So that CO2 may dissolve at a different temperature than the adsorbed from the background. Maybe.
And these are possible adsorbed impurities on our surface. We can have hydroxyl from water. We can have adsorbed oxygen from the gas phase. Even water dissociated fragments. So these can also react from this with this formic acid, adsorbed formic acid, molecularly adsorbed formic acid, to form different species like this.
Okay.
So impurities, and again this reaction is very similar to this step, the same step here. Formate ion dissociate into form carbon dioxide and adsorbed hydrogen, and yeah, that's it, I guess. These are some other fragments that can desorb, like, so for example we have huge water
So
like
standard background reactions that
Yeah.
happen for each sample and
yeah,
okay.
yeah.
I have a question related to Aaron's talk.
Okay.
So the reaction number 2, reaction number 2 here,
Yeah.
tells that the formic acid decomposes at perovskite.
Yeah.
And in colloidal experiment that Aaron was bringing up, it dissociates on formate and proton, but it doesn't break further. So which conditions would prevent decomposition of the formate or formic acid? What should you, like, right now perovskite works as a catalyst for decomposition of formic acid. If we do not want it to decompose, if you want to keep it, what should we do?
On the perovskite.
Yes, yes.
On the Aaron's case, I think you have hydrogen ions, right? Hydrogen.
Or Aaron had the ammonium or whatever.
So ammonium
cations.
Yeah,
And
cations.
enrich it with cations.
So those ammonium cations can release hydrogen.
Uh-huh.
So it can act as a proton donor and just stabilize the formate ion to form formic acid. So it can dissolve something like that.
Uh-huh.
But in our case, so
It seems that it's decomposing in anything, that stuff. And metals, metal oxides, is always decomposing apparently.
But if one would co-dose formic acid and this ammonium stuff, would they would they stabilize each other and prevent from decomposition?
Right, yeah.
So it's too.
but if it has the right temperature, here we have the energy, activation energy. The when you have the submonolayer coverage, we needed like 600 Kelvin of temperature for the decomposition, and up to that temperature it was stable at vacuum.
Okay.
That means we don't have that kind of a huge hydrogen source, but
Mhm.
still without that hydrogen source it was possible to desorb that one.
Okay, so it's stable up to 600.
600, but 600 Kelvin at that conditions.
So for the last step of this main reaction, here is like 600.
Yeah, yeah.
So until you reach this temperature, it will stay in this form.
Yeah, yeah. With perovskites.
Uh-huh. Yes. More questions to Timon? More questions?
So I don't know if there's any system where it absorbs only molecularly, I don't know. I don't think I've seen that somewhere, but on gold surfaces, something totally not magnet.
Yeah.
It seems to always dissociate.
Mm-hmm.
And even copper is not very reactive actually, right? That still seems to
Dissociate.
dissociate. So in copper, there's the oxygen story, I think, is the copper mechanism. So the oxygen seems to promote the process.
So what stands out in formate on the formic acid on perovskite compared to other materials?
What's the?
Is there something special, or something?
This is
surprising?
because you suggested it to do it. That's the only reason why
Okay, but
there was no real motivation for me to do that now.
okay.
Unless it is barely stabilizing that thing, right?
Well,
that was known from the literature.
So in the previous paper, the perovskite was going through decomposition. itself if you go to higher temperature.
Hmm.
Would the formic acid prevent perovskite from decomposition?
Yeah, exactly. We have the according to OJ, we have some stability. Like with the formic acid layer, we have some stability because if you compare the OJ spectra.
Let me bring up the slides.
The effect is not so large, right? It's 50 Kelvin, or how large is it?
But after this thermal ramp, so we did like a thermal ramp of 100 to 750 Kelvin. With that thermal ramp, we have similar structures changed a little bit. That means if you see the intensities are quite different, but still we have the perovskite structure here. But without formic acid layer, we have the structure is completely decomposed. Without the formic acid layer, the structure is completely destroyed. So we don't have the perovskite anymore. So with the same temperature, we have some improved stability. That was the main thing, I guess.
Okay, yeah.
But you cannot really quantify it, right? By how much?
It's like just qualitatively seeing the OJ spectra I was telling. So if we have the same spectra for the before and after the formic acid adsorption experiment, that means it has a thermal ramp of like up to 750 Kelvin. We have a certain amount of perovskite left over, like because we have the similar kind of peak pattern here, but here the peak pattern is quite different. So as you can see from the OJ, it's similar kind of a thermal ramp, but after that thermal ramp, the film seems to be completely destroyed.
Okay. Okay, so formic acid
have somewhat stability.
allows perovskite to exist at higher temperatures, prevents it from decomposition.
But by how much? You have no data for that.
It's kind of qualitative, but just by looking at the OJ spectra,
I
you
don't
can
know
see.
what you do that actually. So the clean system is decomposing what at 480 or something?
Yeah, start to decompose at 480 or something, I guess.
It might be good to estimate.
The starting point of decomposition.
I don't really have the data for that as I'm afraid.
You also compare spectral when carbon dioxide is filled in the vacuum, filled into the chamber.
Yeah, with the carbon dioxide too. With the carbon dioxide also, we have decomposition of perovskite, but the temperature is somewhat lower than with the formic acid. So with carbon dioxide, it starts to decompose around again like 530 Kelvin. But with formic acid start to desorb around like 600 Kelvin. And after desorption, here in this experiment we didn't detect the decomposition fragments because we were trying to detect the dissociation fragments of formic acid instead of decomposition fragments of the perovskite. But the structure somewhat like after carbon dioxide TDS also we had similar kind of OJ, but I don't have it right now.
So it seems carbon dioxide also stabilized the process.
It's not stabilizing, it's kind of, it's not like perovskite. So after the carbon dioxide adsorption study, we don't have this peak pattern. It's much closer to that one. So if you see the OJ here, this double peak iodine, we don't have that over there. So it's kind of, and also after, so this we have one, but I still again I don't have that here now. We did TDS like so. This is the first trial of formic acid dosing, and we dosed formic acid into the chamber, and we just ran the sample temperature and detected those fragments. And after that, we have somewhat dissociated like formic acid structure, not completely, and we dosed formic acid again. And we had a similar kind of peak pattern, the TDS peak pattern. That means we have somewhat like the perovskite structure is not completely destroyed. And these intensities are kind of different. We have a little bit high intensity here, and we have a lower intensity here, but still we have the same pattern. So that means we have some stability introduced with the formic acid adsorption.
And I do have a suggestion for the title of the paper. Formic acid protection enables perovskite solar cell to function in extreme conditions.
Extreme conditions.
Wouldn't it just be a matter of time then? Because the formic acid is still just coming off.
We may find
We need high
solar
temp-
cells at 700 Celsius.
The
Maybe like
decomposition rate is smaller if he puts formic acid on it. Right. So that's stabilizing it somewhat apparently. But we don't really know how much.
need to
Right?
do
So what's the
some-
difference in temperature is. So he took also blind experiments just on the substrate, right? Because if you warm up a sample hole and everything, you get everything dissolving it eventually. So that's why he took a blind, right? You have done that with formic acid also? Or-
yeah.
So you just put in the substrate and without the perovskite on it. And it looks different than that.
And also we just adsorb formic acid on the lead iodide films just to see whether there are any effect of lead iodides. And lead iodides, we don't see these high temperature peaks. We only see the lower temperature peaks. So on lead iodides, formic acid adsorbed somewhat molecularly. And on lead iodide and ITO substrate, we tried both substrates, and it has peaks in below this region, below 400 Kelvin, not like this kind of high temperature. So that means formic acid binds strongly to the perovskite layer.
Okay, so it prevents this methylammonium cation to decompose and leave. In
I
perovskite.
don't remember exactly anymore how the blind spectra look like. But it even decomposes on the glass or not? The formic acid.
It
looks-
didn't decompose on the glass, I guess.
Sure.
It's just molecularly dissolved.
Yeah, I don't remember anymore. The,
Lower temperature peaks like this. I think it prevents the methylammonium cation, but we need to do more experiments.
Yeah, but it's a good hypothesis and,
Yeah.
and good like strong thing to mention.
problem is he will leave, so I don't think he will have much time to do any experiments, right? So he would like to graduate. Otherwise, we should look for water desorption and CO2 desorption, right?
With the formic acid.
Yeah, and then I don't know if we can quantify more.
Yeah, if we have water desorption and hydroxyl and the formic acid dissociation fragments like methyl, we didn't detect that one with this one, that's why we couldn't exactly tell, but we can detect those fragments too. At the same time, we can detect only 4 fragments with proper intensities. So if we want to do both, then we have this part, like we have the dissociation fragments of formic acid, but if we want to detect the desorption fragments of the perovskite layer, we need to do a different experiment. So we can simply synthesize the perovskite layer and adsorb a formic acid layer like this, and then we can try to desorb it. We can just do the thermal RAM, and we can detect those dissociation fragments of formic acid, and we can see which temperature those fragments are desorbing. We can do something like that.
Okay.
So with carbon dioxide, we did that kind of an experiment with carbon dioxide, and when we do the thermal stability test, also we just increased the temperature of the surface, and we detected those dissociation fragments of formic perovskites.
Okay.
With this one, we were interested in the formic acid desorption fragments.
Okay.
Yeah. So one step.
What are your own questions to
Right.
this work and
Yeah,
maybe
yeah.
to the theory? What is not clear? What are the challenges that needs to be addressed?
Oh, we had a slide, but it's in a different.
Just tell verbally.
So my main question was with that passivation layer of formic acid, whether it affects strongly to the electronic structure, band structure, or any kind of electronic structure that is useful for the industrial application of formic acid, the perovskites. So if it affects strongly to the electronic structure of perovskite layer, then it won't be useful to have a passivation layer of formic acid. So
Okay.
yeah, that was the main question.
And
I had-
other questions in the dynamics and mechanisms of adsorption and reaction.
Yeah, the main problem in that case was whether the formic acid dissociate on impact or whether it adsorb from the surface molecularly and then just diffuse and dissociate.
Okay. Yep. Excellent. Dissociate on
Impact.
Yeah, what is the activation energy that dissociates?
In impact, if it is dissociate in impact, then it will be a lower one. But if it is on like when we do the thermal ramp, then it will be higher, I guess.
I mean, also the fragment seems to be binding pretty strong to the surface.
Yeah.
If you see that dissolving at 600,
600 Kelvin.
so I guess you could maybe get the binding energies of these fragments.
Mm-hmm.
For example, something like that.
And actual fragmentation patterns are not like exactly known because these fragments, we may have these fragments, but not all the fragments, maybe.
Okay. Yeah. Very good. Well, part of the answer to your first question was in the presentation by Aaron. So if it is complete coverage of surface by combination of carboxylic anions and ammonium cations, or whatever, ethyl ammonium, then the gaps, the frontier orbitals are not from surface, but from the bulk, and they can participate in electronic and optical applications.
Okay.
If it is only one, maybe it will be a trap and a contaminant. But if it is complete coverage, there are preliminary results that it will be fine.
Okay, nice.
So there's a concentration dependence on
Electronic properties. If there is only one ligand, like formic acid on the whole surface, it will probably work adversely. It will work as a charge trap. But if it is homogeneous coverage, likely the all charge carriers will stay inside the material and participate in either optical absorption emission or like charge transfer for photovoltaics. Well, it's a great question to ask.
That's another parameter in the game, right? So the concentration dependence. That would take forever to figure that out. Right. So
But theoretically, we can just put a layer and then it's like.
at the moment you have almost multi-layers, right? When you start.
Yeah. So I dose.
If it was just half a lingua instead of 20 linguas, does it look then totally different? I don't know. The TDS.
But for computation, it can be checked.
Yeah, usually we needed
It's
like.
probably even simpler than checking binding energies and absorption mechanisms. It's like as simple as possible
Okay.
question. More
What
questions?
what is the water doing, right? Because we have for sure water and
Yeah.
on the surface.
So with in the carbon dioxide study, we see the co-adsorption of water with carbon dioxide, which can form some stabilization, carbonic acid formation. But here with formic acid too, we might have some effects with the impurities, like mainly water. So water can have some kind of effect of the adsorption desorption process. So it is another question, like because of the impurities.
More questions to Dylan? If not, thank you once again. And let's see if some of your questions will be answered by Dr. Yulhan. I think you cannot do advanced just to comment.
So just in case someone haven't heard about this research, so this is how we create the model. So basically we start from the crystal structure from bulk, and this is for the concrete phase perovskite, and then we just create a unit cell and we cut it. Because once we cut it, we have two surfaces, and we add 15 angstrom vacuum to each surface. Like in this case, we cut it so we can have a top, we can have a bottom, and we add the surface. And also in our calculations, we fix the bottom layer. So I did this for different directions, and I focus on 001 top surface because this one is the most reactive one. So here, I just put the formic acid at the top. So basically here is a binding with the oxygen of the formic acid and the metal. So I didn't try a lot of initial configurations, but I guess this one is quite stable because in addition to this bonding, we also have a hydrogen bonding between this hydrogen molecule and this ion. And here is the binding energy.
So that is a molecular adsorption.
Yes.
And what's the definition of like in your definition of binding energy compared to definition by Aaron? Positive binding means it does bind. It's energetically favorable.
It's because the larger the number, the stronger the binding.
Okay.
That looks pretty large from my test.
So
I don't know what desorption temperature that would be much higher, I guess, what you see, I'm afraid. 62 kJ per mole. What was the CO2 again?
CO2 was 170 something.
Yeah, but it dissolves at 700, right? And you are stuff dissolving at 200.
And this is, I think it's kind of 62, 200 around.
That looks kind of large. I need to calculate the desorption temperature for that.
and also right now I use spin restricted DFT. So
Because,
in the paper we use spin orbital coupling. So if I apply spin orbital coupling, this number may be slightly smaller, I guess.
Yeah, we haven't really calculated the binding energies, right? Do you have a peak at, where is it, I think?
It's around 200, the molecular desorption
Yeah.
rate.
So we should figure out what binding energy that is. I would guess like 40 or so maybe, I would guess.
For 200, yeah.
So it's not totally different than your number, but I think it's smaller, I would guess.
I remember in the paper you mentioned binding energy is like 45 to 50.
Maybe I put it in the paper actually.
Yeah.
So we don't remember.
And right now, the surface is, you've told that it is mostly reactive surface.
Right.
Which may, well, we do not know what is going on, but it may self-heal and reconstruct. So it's, right now it is also a hypothesis that we expose most reactive surface. In less reactive surface, it will be much smaller binding.
Well, that's already an interesting result, right? So you can give us the adsorption site, I guess, and stuff like that. Did you try different adsorption sites? Or?
Not really, but I guess this one is reasonable because what kind of other absorption site can you think of?
But you have 20 different adsorption sites, and I think, right? No.
Well, if you select just slightly change adsorption site which is nearby, and if it is wrong by one during optimization, it can jump.
So it's pushing it to that. Okay.
Because right now I guess this configuration chemically it is reasonable, right? So oxygen goes to the metal, hydrogen goes to the iodine. So next I try just put water. And this is very, very stable, I guess. This is the binding energy, it's like 110. So here, still we have the oxygen metal bonding, and this is the water. So it's kind of like from a ring structure. So this is one member ring, this is one atom, second one, third one, fourth, fifth, and sixth. That's the reason why this geometry is very stable.
So then you have a clean surface, according to that. If there would be water on the surface, your binding energy would be much larger, your dissolvation temperature would be larger. It seems not to be the case. It's a little strange. But there is for sure water on the surface. Well. So it's increasing the binding energy so much. We should see another peak then or something like that.
What would be the temperature for this binding energy? What would be
That is a pretty large, but I don't know, is it a 600 Kelvin or something like that, right? 500 something, I don't know, I have to calculate the temperature. You would need this, then you would see a second molecular peak, right? The second parent mass. There is a second peak actually in your data, right? At high temperature.
Yeah, there is another.
So we thought that what we recombinate,
Recombinated desorption.
maybe it's just the water stabilization. So he has a second peak actually.
Okay.
Maybe it's the water, not the recombination. So given all the water impurities, that is maybe more likely than.
Then recombination.
Okay, that may explain the second peak. What is CO2 doing? Did you try that also? That is water, right? Water co-absorption.
Is this the water?
Can you co-absorb CO2? What is that doing?
Do you mean by adding another CO2 molecules? into
Just
this?
CO2 and formic acid, so I don't know what this. Because these are the two main impurities, right? Apparently CO2 and water.
Oh, you mean like having CO2 and formic acid together?
Yeah.
Whether the presence of CO2 will...
If that is doing the same or something, I don't know.
No, because if you have CO2, then oxygen should repel from iodine, right? So there is, you cannot form a like ring member structure with CO2.
So that would not affect the binding energy of the formic acid. But I
It
don't know.
will decrease the binding energy for formic acid, yes. Because this kind of structure is not stable.
So what I don't quite understand.
Is it, what you're telling
That
me
would
is
chemically not make sense or something, I guess.
the presence of carbon dioxide will not help formic acid to absorb stronger.
Ah, okay.
It's just my guess. I guess I can know some calculations.
Because that would be relatively simple to do, I guess.
Okay, so for this one, I just place a hydrogen into this position, so very close to iodine. And after geometry optimization, because this hydrogen structure, and here this is the hydrogen. So I also try another configuration by adding hydrogen right here. So then after geometry optimization, it's just go to the formate.
Huh. So it is very unfavorable geometry. Negative means it's like it's going to repel.
Yes, but guess in this case maybe the formula to calculate the binding energy is not very accurate, because I use to the energy of this formic acid.
So what is that showing? I don't. So what have you done here? That's
That's the question.
Let's probably let's increase, zoom in the figure.
so what's the difference to the last?
Someone here in the audience should speak chemical language. There is a monodentate, bidentate.
Ah,
what's
is it different? That's
the third one?
Polydentate.
Polydentate.
Okay.
So previous one was monodentate,
Ah, okay.
and this one is bidentate.
Okay. I think that's what is usually preferred in the literature, I think.
It is
That
Cuneiform chelates, like
if I remember that.
chelating, yes.
Yeah.
Yes.
I remember that correctly.
So bidentate is not stable in this case.
Why is that the case? I mean,
I guess this time I just breaking the carbon-hydrogen bond, so we have a hydroxyl group and also this CHO. So here this CHO group, the carbon bonding to the iodine, and the hydroxyl group bound to the metal.
And it looks more stable. So when formic acid breaks, the binding energy increases. In one of the previous is monodentate, 2 slides back or 3. One more. So it, and one more without water. Yes, here it was 62 when it was intact, and when it chemically broken onto HCO and OH, it becomes, oh no, it is negative. So it is not favorable.
Right.
Okay.
so it does not dissociate?
Guess this means this structure is not very likely to exist.
This choice of initial geometry doesn't seem chemically stable. There is a very big human influence of how you construct initial geometries. If you do something wrong, it probably will correct you, but not always.
So what's the conclusion? That it does
Well,
not?
we need to screen several initial guesses,
Uh-huh.
several initial binding geometries, and select which of them are chemically more stable on one hand, and which of them give binding energies that in reasonable agreement with experiment. So there are 2 criteria.
So can you figure out if it dissociates somehow or not? Or these are all molecular adsorption geometries or not? So far?
Well,
this is kind of dissociated geometry.
this one is just screening of the static configurations.
Okay.
Geometry optimized total energy. While for more detailed exploration of the reaction path, one would try molecular dynamics, as we tried to do last time, but it is more expensive. Here, one goes into a quicker shortcut to do simple things.
Yeah, okay.
Basically what I did right here is I have this molecule and I artificially break them into different fragments and I attach different fragments to the surface.
Compare the binding.
Right.
Okay.
So it's not the most right and most best way, but it is the quickest way.
Okay.
It's like
Okay, I've seen
100,000
that,
times quicker than other
Yeah,
things.
okay.
So this is another geometry. So here this is a hydroxyl group. The oxygen is bound to the metal, and this is the CHO. So there is a hydrogen bonding, I guess, or short contact from this carbon and to this iodine. So here the distance is 2.2 angstrom. This gives a more negative
So
bonding
it's
energy.
least stable.
No, the next one is at least stable.
Okay.
So this time I have the CHO fragment, and I put the hydrogen of CHO closer to the iodine. But after geometry optimization, we see the breaking of the hydrogen carbon bond. So here we have a carbon monoxide, and this is the hydrogen. Here is the hydroxyl.
Is it possible for that ammonium to take any more protons? Because instead of binding to the surface, that hydrogen or whatever could diffuse in.
Well, this is a positive ion, right? If you have a hydrogen, that means hydrogen is proton, right?
Yeah.
So true positive ion.
Yeah,
That's not favorable.
that makes sense.
What's the total number of atoms in the model?
Total number of atoms.
Uh-huh. Just roughly, is it like
Guess
100 or 1,000?
100.
Okay, so it's affordable for molecular dynamics.
Yes. This is the last line I have.
Maybe it's if you want to go over.
Here, this is a summary of the finite energy I have for different configurations.
So with water is more stable.
Yes.
In your previous work, there was a guess of presence of like cavities, special shape of defect. And right now it is not needed. Like in previous work, the binding energies were diverging very much from experiment until we guess that there is a cavity-shaped defect.
That is pretty close to the TDS, I guess. Well, not really quantitative matching, but I guess it's close.
Molecular desorption.
Yes, molecular, and then you have a high temperature.
High temperature, those two.
So the first two numbers would maybe match, I guess, the experiments. You have to calculate binding energies, right? Apparently I put a number in the paper, but I don't remember what's that number actually was. But how to explain the other mass as well, the dissociation? That seems not really to match your calculations at the moment, right?
Well,
Yeah.
we can launch molecular dynamics and see what happens, and if maybe just share results by email or maybe meet another time if it would be something.
I don't know how much of an effort it is.
Well, it is not much of human effort. You just it's a lot of computational time. You launch it and wait for whatever a month or maybe 2 weeks.
Okay.
So you may prepare several initial conditions and run them in parallel and then select which one.
You have enough computer dollars to do that?
We are done. We spent like 20 million this year and went into the negative.
20 million computer dollars. Okay.
Not dollars, compute hours.
Oh, that's okay.
But the local CFAST is for free. It's just not as strong as the national facility.
So you can use a cluster here on campus for free.
Yes.
Okay, we can do that.
So it's a little slower, but we have some backup.
So we run some dynamics, I guess, molecular dynamics. So I
It's
know
not-
Thielen has time to collect some more data and to show that it will work out. But
I can try the dissociation in the formic acid. What kind of temperatures that perovskite dissociate?
But you have source data on it.
It's for the with formic acid we don't detect the water desorption, carbon
water,
dioxide.
yeah, okay.
The other
Water.
fragments like the formic acid, like methyl ammonium or CH3 fragments, we didn't detect those fragments.
Okay. So we can maybe run 2 more samples, I guess. So that's basically it, right? And we have
Depending on-
Christmas.
Guess I have a question. So if we make sure there is water on the surface, I guess maybe is there any possibility that the water will react with the pull hydrogen from this fragment?
So, in the same way as it was before, so we can guess formation of this Zundel cation H3O plus. so that water will pick proton from carboxylic acid and find a spot, like adsorb somewhere simultaneously.
Really, I guess my point is, I guess maybe the feature you observe in the mass spectrum is mainly due to chemical reaction between water molecule and the formic acid.
Okay, so for what masses should he look? Any idea what is formed? So you can just dial in a mass on a mass spec to look for it. But we have to know what mass it is, right? Otherwise. So if we can figure out what he should look for, then we can do that, I guess.
Okay.
But we can measure with 4 masses at a time. Takes a week. So you get 4 masses every week.
So you cannot, it's not like, it's multi-channel, but you cannot do like all channels at once. You pick.
The noise will be as crazy. The intensities are not large enough.
Uh-huh.
So
4 seem to work, maybe 6 is working, I don't know. But if he's heating up the sample, then the sample is dead, right? This is one shot. This is one experiment and then the sample is dead. So this is somewhat unusual. They usually do not run experiments like that.
It's same like quantum cryptography, where measurement breaks the sample.
Yeah, exactly, yeah. So that makes it very time consuming to really characterize that system. Yeah, let us know for what masses we should look for, right? So the idea at the moment is just to look for water, I guess.
And there is dissociation, like we know with the thermal stability test, we know what kind of temperatures it start to dissociate. With the formic acid also we can do the same test. What kind of temperatures it dissociates. At the same time we can detect water.
Yeah, but that is the same experiment, right?
Yeah, it's the same,
Same
same thing. Water and those fragments.
Let's thank the speaker. We can keep chatting if you have more.
We have already some results which are matching more or less.
So you have some zeros order.
I guess it might be enough already for publication, I guess, but not a very good one.
Very encouraging.
So the more we get, the better will be the paper, I guess, right?
Okay. So we will maybe collect a little more numerical data on this one.
We can start writing already if you like.
And
Now you have my text just because the molecular channel seems to fit more or less, so in that part, this is already finished, I would say, the molecular absorption.
Actually, even the molecular absorption temperature seems to be a little bit lower. So the with water, like 109 kilojoules per mole, it can be a little bit higher than that in this.
It seems not to perfectly match quantitatively,
It's
but
like it will be in the range of 150s, I guess, 50, 60
yeah,
maybe.
we have to, I don't know, we have to do the calculation for the.
And the smaller temperature desorption energy seems to be much closer. It's like 60s
We
to.
just use the red hat equation, so you just put in the peak temperature and the red hat, and then you get a binding energy.
So I guess it can.
Yeah, so that is in the first paper, I think.
Right.
In the supplemental, I think it's explained how to do that.
Yes.
So you can just get the binding energies in that fashion from the TDS. But nobody knows what the prefect is, right? Depending on what prefactor you put in there, you can get any number. Right? No, pretty much. Unless you calculate the pre-exponential somehow for the desorption.
yes,
There is a way to do it, right?
there is a way. It will be questionable how
precise.
yeah. So we can wait, like heat it up instantaneously, assigning momentum to each ion, certain temperature, and then wait how long it will take until it starts departing. And then take this time from beginning of simulation until departure.
So
as inverse of the rate.
That's how you get up.
I know on my
Yes.
the bin I keep on my
So
computer.
if it is
I have-
bound, it will never depart. If it is easily desorbed, it
commands
will
I keep-
instantly. If
I
it is
put them on
in
the
the
bin
middle,
on
it will
first.
find maybe a little better spot and then go away.
Okay. It's how precise is that?
Qualitatively, it agrees with expected trends, but quantitatively, we never went to detailed qualitative analysis. It's would be a lot of collection of data. Each data point is independent molecular dynamics simulation, and each molecular dynamics is.
But there's also a quantum mechanic way to calculate it, right?
So
Somehow.
say
Yes,
See, what is it? What's the RRMP something
Energy
theory?
but then
See,
then you need to guess or compute potential energy surface.
yeah.
And formally, it depends on like.
or no, this would be like the
degrees
text
of freedom,
file.
Okay.
which is too
For
many.
the technical-
If you select
Or your states
one reaction,
states or energy pop. So you know, like the first column is your band, your second
then
column
there
is
is
your
a big
energy,
question.
third
Did
column
we
is
select the right
observation.
direction, plus right direction coordinate? So it's
So this group here, so
it is a good method to scan.
So these numbers
potential
refer to
one
column.
direction coordinate, but
so if you wanted to subtract, like if you knew what your Fermi number was,
is chosen.
you could say
Also very
take.
decisions.
So Anka is just a command, so you put in print first column. And then the second column would be column
We
one
have
times
submit
column.
have a one paper in.
And then you would read in like your energy pop, and then you just make the
direction
calculation.
of this.
So if you wanted to do this, you would just do one.
Okay.
Just have
And
to use
how
one.
was it going with it?
Yeah.
Well, it was
Yes,
refused from Jets, and instead of going down, we decided to go up.
It's into science now, or what?
No, just nature
Right.
communication.
Column one.
It's not refused
Column
for
one, how you'd want it.
4 days.
So it would be
It's pretty good, I guess. They have a pretty
Because that's
standard.
just about the
minus
weekend.
whatever number
Yeah,
it
we
is.
can So we can compete for getting
And then
publications,
you
but
want
we
to
can
drop
compete
patients the same,
for
so
books
you
and
would-
for rejection.
You can submit it at Christmas and it will count for
And then you tell it to read states or whatever. And then this way states.
Yeah, start writing something in modular parts. That would be one option.
Right.
Paste them, standard things for
Mhm.
methods.
See what? See.
Copy, paste.
Yeah,
So
yeah,
standard
the methods
template.
section you can
Yep,
start
then you
writing
just
something
wanna
like that. I don't know
this
where
your
we want
states
to
file.
send it, but I guess we have no
Or like copy that in
limits
the states
this
before,
time, right?
when,
Well,
for your
probably before he departs, before Christmas.
Yeah, to what genre?
this is how I do
Well,
it.
journal.
So the length doesn't really matter, I guess, but we are not limited to 4 pages or something, right? So at this time, I guess. So I haven't really thought about where to submit something.
If you cannot justify it for a fancy journal, then
I don't think so, not really. So you can always try, I guess, but if you send it to a fancy journal, then you have to keep the 4 pages, which is always stressful. Because usually
I
pages
was just
get
so
into
every time that you do a new column, you just put a
Journal
count.
of Physical Chemistry C, which is to
Here these two
what?
columns.
Journal
JPC?
of GPCC.
Oh yeah, so
It's fine.
journal of
Physical Chemistry C.
so yeah, if you wanted
Yeah, then
to
you
like
don't
to
have
do
a page
Oh,
limit, right?
okay.
Yeah, it's fine.
But I don't
The impact.
need to.
for this one no,
That
because
is a
for
pretty
eFirm you
decent
just want to
journal,
subtract.
We could try some materials.
But if you just have, like, any
They also do not have limits.
Formatted text
They are
or data file that you had.
They are more
Let's
synthesis.
say you wanted to
usually,
add another column,
synthesis, which we can't really do with,
2 columns that you wanted to add together.
I guess journal physics
Like you would just
pretty
do something
good,
like
I guess.
this.
Try that. Then you can write as much as you like.
Okay.
I think there's a limit of 12 pages or so, right? Printed.
No.
Otherwise they charge you money after the
For
talk.
physical transforms in polar.
I have forgotten
Maybe
at the beginning to invite
that
everyone
counts.
to
So
congratulate Aaron.
How do you fix
Although
the
he's
values?
busy, he got his paper in GPCC accepted today.
No, that makes sense.
Aaron, we congratulate you.
Okay.
He told me once journals I have to pay if it's longer than 12 pages and they charge you?
We are congratulating you. We are
They didn't charge
Oh,
you.
maybe they changed that rule.
It was like 50 pages.
50?
Well, in double spacing. Not
Yeah,
in
they
double
printed,
printed. We'll see after getting the proof.
But 50 is more than 12, I guess.
We had around 38 or something.